Alright, so as promised, here's our example that we're going to do. Let's do it one way. So Fubini says it doesn't matter which way we do it. So let's actually do it with respect to y first. So we're going to go from 0 to 2, 1 to 2, our function. And then we got dy and then dx. So for our first integral, our inside integral, we have x is a constant. We can go and integrate this right away. So we go from 0 to 2. We integrate, x is a constant, so the integral of x squared is x squared y. And then we have minus 3, and we add 1 to our exponent for y, and then multiply by 1 over the new exponent. And we have to evaluate that from 1 to 2, and then we have a dx. Alright, so then we're going to substitute in for y. Now remember, this is y equals 2 and y equals 1. So here we go, we got 2x squared minus 3 halves, and y is 2. And then we have to subtract when we substitute in y equals 1. So that's x squared minus 3 halves. And we still have to integrate with respect to x. Let's simplify first and then we'll integrate. So we got 2x squared minus x squared. So that's an x squared. And then we have minus 3 halves times 4. I should really simplify that. And that just becomes 6, right? And then we, remember I distributed, that's how I got the x squared. And then this becomes a positive 3 halves. Okay, so we're still working on simplifying. We get x squared, and then this becomes 12 over 2. So then we get a minus 9 halves dx. Now we're ready to integrate. So the antiderivative of x squared is 1 over 3x cubed minus 9 halves x. We evaluate it from 0 to 2. And remember, this is x equals 2 and x equals 0. So we substitute in first. And then we have 9 halves and 2. And then we subtract when we substitute in 0. Okay, we get 8/3. And then minus 9. And so this becomes 27 over 3. And so we get minus 19 over 3. Okay, so that's our answer. And I want to challenge you to see if you can get the same answer if you change the limits of integration. So in other words, if you integrate this, do you get the same exact thing? Alright, and that's up to you. Okay, so we can use Fubini's theorem to help us out. Sometimes one integrating with respect to x is easier than with y, or vice versa. So I guess we're just going to do a remark and then actually show it. So we'll do a remark. Sometimes the order is easier for a certain way. So what I mean by that is either dx dy or dy dx. One of the two is going to be easier. Let's actually do an example here where we can show that. So we're going to start out with our area over R of x x cosine xy dA, where r equals 1 to 2 cross 0 to pi. Now this notation means these are the x values and these are the y values. Okay, so we're going to try out this first way. Basically, you just pick. So let's pick where we go from 1 to 2 first, and then from 0 to pi. Keep the inside the same, and then we're integrating with respect to y first. Okay, so once we do that, we remember that here we have x is the constant. Okay, however, we still have to do a u substitution. So let's move down here. So in general, if we didn't have any limits of integration, and then we'll put them back in up top after we do the u substitution. So the thing that's botching it up that we can't do the integral for is this xy. So let's do u equals xy. Then we do the differential. Now remember, x is a constant, so it's along for the ride. The derivative of y is dy. And do we have an x dy there in our integral? Oh, let's highlight the other one. We definitely do. We have an x dy in there right away. So let's substitute in. So we got, instead of cosine of xy, we got cosine of u, and then instead of x dy, we have that it's du. Now the integral of cosine, so let's see, is sine u plus c, and then we substitute back in, and that's what the integral is in general. So we can go back up here and substitute in. So we got 1 to 2. We know what this antiderivative is. It's just sine xy, and then we had to evaluate it from 0 to pi. And we still had to integrate with respect to x. Alright, so that's our integral, the sine of xy, and then we don't need the plus c since we're doing the fundamental theorem of calculus. So let's say that that equals star. We'll move all the way down here. We get the integral from 1 to 2. We do the fundamental theorem of calculus. We substitute in, remember this is y, is pi. So we get pi x minus sine of 0x dx. And we can substitute in, or simplify rather. We have sine pi x minus 0 dx. And so our integral just becomes sine xy dx. Alright, so we have to continue on and integrate this. And same story, we have to integrate, but we have to do a u substitution still. Oop, and then my, so inside my sine is just pi x. So I copied incorrectly. There we are. We're going to do it in general here. We get u equals pi x. So the differential, we get pi dx. We don't have a pi dx in our integral, so we're going to divide by pi. There we are. And so now we can do the substitution. So in general, so without our limits, we have this integral. We're going to do the substitution. So we get sine of u, and then 1 over pi, and a du. And then the integral of that is 1 over pi, and we get cosine u, but then we have to make it negative plus c. We're going to substitute back in for u. And there's our integral in general. So let's say that this now equals star. We're going to continue on down here. And we know what the antiderivative is. It's 1 over pi. It's the antiderivative, but now we have to evaluate it from 1 to 2. So first we're going to substitute in 2. And we get cosine of 2 pi. And then we have to subtract when we substitute in 1. Now cosine of 2 pi is 1. And then minus a negative becomes positive. And then cosine of pi is negative 1. So we got negative 1 over pi minus 1 over pi. And then that gives us minus 2 over pi. And so here we have a completed version of this. But remember, I said depending on which way we have it, we do the order of operations here with the integrals. Depends on if it's going to be easier or not. So that one wasn't so bad. Let's see what the order is if we do it the opposite way. Okay, I'll see you in the next video.